Welcome to Reality School. In this video, we'll go over how to save AR content in a scene and restore it at a later time. When completed, our app will have a browse and scene mode. When the user switches to the scene mode, there is a button to save all AR content in the scene to the local file system, and another button to load previously saved AR content. This video covers several advanced topics, so please take your time and make sure you understand each step of the process. I'd also like to point out that this video references Apple's sample project on saving and loading world data. In their project, Apple focuses on UIKit and SceneKit. In this video, we'll focus on SwiftUI and RealityKit. A link to their project page will be in the description below. Before we get started, this is the hardware and software used in this video. If you are using anything older or newer, you might have to make some adjustments to your code. We have several action items for this video. First, we'll refactor our codebase to improve organization of the source code. Second, we'll create a SceneManager observable object. Next, we'll create an updatePersistenceAvailability method. After that, we'll create a SegmentedPicker to switch between control modes. Next, we'll create a BrowseButtons view and a SceneButtons view. After that, we'll create a lazy variable for our persistenceUrl. Next, we'll create a ScenePersistenceData property in SceneManager. After that, we'll create a ScenePersistenceHelper class with type methods to save and load a scene. Next, we'll add functionality to the saveScene type method in ScenePersistenceHelper. After that, we'll add functionality to the loadScene type method in ScenePersistenceHelper. And finally, we will update the codebase to allow placement of 3D models loaded from a persisted scene. So without further ado, let's get started. For the first action item, we'll refactor our codebase to improve organization of the source code. Let's take a look at ContentView.Swift. We see a lot of our code belongs to a different struct called ARViewContainer. Let's give this struct its own Swift file. Create a new Swift file and call it ARViewContainer. Cut and paste all code belonging to the ARViewContainer struct from ContentView.Swift into ARViewContainer.Swift. At the top of ARViewContainer.Swift, import SwiftUI and RealityKit. There should be no errors when we build the project. Go back to ContentView.Swift and remove the import statements for RealityKit and ARKit. We no longer need them in this file. For the second action item, we'll create a SceneManager observable object. At the bottom of ARViewContainer.Swift, create a new comment using mark and write persistence. Most of our persistence code will be below this comment. Create a new class called SceneManager and set its type to observable object. In this class, we'll create two published properties. The first property will be isPersistenceAvailable, which will be a bool with an initial value of false. The second property will be anchorEntities, which will be an array of anchor entities. We'll assign an empty array to the property. This property will keep track of anchor entities in the scene. Note that we only add an anchor entity to our scene when we add a model entity to our scene. Our SceneManager is now complete and we can pass it into our environment. To do so, we'll go to the main entry point of the app and create a corresponding state object for SceneManager. We'll pass this state object into our environment using an environment object. We'll also navigate to our ContentView.Swift and pass in a SceneManager object into the environment of the Content View preview. In our ARViewContainer, we can get access to our SceneManager instance by using an environment object. We are now done creating our SceneManager. For the third action item, we'll create an updatePersistenceAvailability method. We'll start off by creating an extension of ARViewContainer. Next, we'll create a private function called updatePersistenceAvailability. The function will have one parameter which will be an ARView. The return type is void. We'll use a guard statement to obtain the current AR frame from the ARView session. We need this AR frame to access the world mapping status. Whenever the world mapping status is .mapped or .extending, and at least one AR object has been placed in the scene, we can set the isPersistence_Available in the SceneManager to true. Otherwise, we'll set isPersistence_Available to false. In order for this logic to work, we have to make sure to update the anchor entities property in SceneManager each time a model entity is added to the scene. We can do so in the place method. And finally, we can call our updatePersistenceAvailability in the scene observer in our makeUIView method. Doing so will run updatePersistenceAvailability for each AR frame. For the fourth action item, we'll create a SegmentedPicker to switch between control modes. Currently our user interface has 3 control buttons, which are most recently placed, Browse and Settings. But what if we want more buttons, for example buttons to save and load persisted AR scenes? For this we're going to create a segmented picker to switch between control modes. In ControlView.Swift, we'll create an enumeration for control modes. This enum will have string raw values, and will also adopt the case iterable protocol. According to Apple's documentation, when using a case iterable type, you can access a collection of all of the type's cases by using the type's AllCases property. For now, we'll create 2 cases, Browse and Scene. Next, let's create a new state property in our content view struct. We'll call this property selected control mode and we'll make it an integer. We'll also give it an initial value of 0. In our control view struct, we'll create a new binding property called selected control mode, which will again be an integer. This binding property corresponds to the state property defined in content view. When we build the project, we get an error in ContentView.Swift saying missing argument for parameter selected control mode in call. We'll use the autofix feature to add a parameter in our control view constructor call. We can now pass in a binding to our selected control mode state property. Moving on, we'll navigate to our ControlView.Swift file and create a new struct above our control button bar struct. We'll call this struct ControlModePicker and adopt the view protocol. Create a body variable and use Xcode autocomplete to help you along. To get rid of the error messages, we'll temporarily use a placeholder text view in the body. We'll make the text say replace with SegmentedPicker. To create our ControlModePicker, we'll do 3 things. The first thing is creating our properties. We'll create a binding property for selected control mode. We'll also create a constant containing all cases of our control modes enumeration. The second thing is to create our segmented picker in the body variable. Remove the placeholder text view and construct a picker. We'll pass in a binding to selected control mode and a text view as the label. Inside our picker, we'll use a for each loop to generate a text view for each control mode. We'll use the uppercased value of control mode raw value as the text for each segment. Note that we're using a tag to uniquely identify each text view. Feel free to pause the video to ensure you understand what is going on. Next, we'll use several modifiers on our picker view. We'll use the picker style modifier to configure our picker as a segmented picker. We'll set the max width of the frame to 400 points and add horizontal padding of 10 points. The third and final thing we need to do for our control mode picker is to create a custom initializer for our struct to modify the appearance of our segmented picker. The initializer will accept a selected control mode parameter which will be a binding property with an integer value. Before we customize our segmented picker, let's assign the selected control mode parameter value to the struct's selected control mode property. Since we are initializing a binding property, we have to prefix the name with an underscore. Next we can customize the segmented picker. There are 4 changes we want to make to the appearance of our segmented picker. 1. Change the segmented tint color to clear. 2. We'll set the text color of a selected segment to a custom yellow color. 3. We'll set the text color of normal, meaning non-selected segments, to white. 4. We'll set the background color of our segmented picker to black with an opacity of 0.25 or 25%. We are now done with our control mode picker struct. To wrap up this action item, we'll call the control mode picker constructor in the if statement in the control view struct. Make sure to call the constructor above our control button bar. Let's run the app to test our intermediate progress. As you can see, we now have our control mode picker showing a browse mode and a scene mode. When switching between these modes, nothing happens. We'll work on that next. For the 5th action item, we'll create a BrowseButtons view and a SceneButtons view. Because our app is becoming more advanced and we're adding multiple control modes, we'll update our control button bar view to enable that functionality. Right below our control button bar, create skeletons for 2 new views. Call them BrowseButtons and SceneButtons, respectively. Cut all the contents from the control bar button view and paste into the BrowseButtons view. Remove the 3 modifiers from the H stack. The BrowseButtons view is complete. Let's work on the SceneButtons view. First, we'll gain access to our SceneManager instance by using an environment object. Next, we'll create a body variable and create 3 control buttons within the body. We'll create a control button with system icon name iCloud. And .arrow.up. We'll also add a print statement that says SaveScene button pressed.
Next, we'll create another control button with system icon name iCloud dot and dot arrow dot down.
Again, we'll add a print statement with a message loadScene button pressed. After that, we'll add a third control button with system icon name trash. When pressed, this button will print clear scene button pressed. To make things look better, let's add a spacer between the save and load buttons, and another spacer between the load and clear buttons. And finally, we'll add our custom hidden modifier to our save control button. The button should only be displayed when isPersistence is true. Since we cut all the code out of our control button bar view, let's fix this. We'll create a binding property for show browse and show settings. We'll also create a regular property for selected control mode. Since control button bar only reads from selected control mode, we don't need to pass in a binding property. We'll create a body variable and add an hstack with alignment set to center. Inside the hstack, create an if statement. If selected control mode is 1, we'll render our scene buttons. Else, we'll render our browse buttons. We'll need to re-add the 3 modifiers to the hstack. Set the max width of the frame to 500 points. Set the padding to 30. And set the background to a black color with opacity at 0.25 or 25%. When we build the app, we should get an error for our control button bar constructor in our control view. Use autofix to update the constructor call and pass to selected control mode. Run the app to test our intermediate progress. When we place an object in our scene and ensure enough of the scene has been mapped, we see that when we switch to scene mode the Save Scene button is displayed. We also see our Load Scene button and Delete button. In this video, we will only focus on the Save and Load buttons. The Delete button will be covered in a different episode. For the next action item, we'll create a lazy variable for our PersistentceUrl. Navigate to ARWContainer.Swift and scroll to the SceneManager class. Below the existing published properties, we'll create a lazy variable for our PersistentceUrl. A lazy variable is great for creating computationally expensive variables using a function that is called only when the variable is first requested. Our PersistentceUrl will contain the URL for the location in which our scene data is stored in our local file system. We'll use a do-catch block to obtain a URL from the file manager. In this case, we'll pass in document directory, user domain mask, nil, and true to the constructor for our URL. We'll also append path component arf.persistence. If we're unable to get a URL from the file manager, we'll create a fatal error with the message unable to get persistence URL and use string interpolation to provide a localized description of the error. Note that using fatal error will crash the app. We're using this to make sure that the developer knows something went horribly wrong. For the next action item, we'll create a ScenePersistenceData property in SceneManager. We'll use an optional data property to verify that scene data can be loaded from the local file system. Next, we'll navigate to our SceneButtons view in ControlView.Swift. We'll add a modifier to our loadScene button to hide it when the ScenePersistenceData in our SceneManager is nil, meaning no scene data is available to be loaded. This is all we have to do for this action item. We can now move on to the next action item. We'll create a ScenePersistenceHelper class with type methods to save and load a scene. Create a new file and call it ScenePersistenceHelper. Import RealityKit. Next, we'll create a class called ScenePersistenceHelper. Inside this class, we'll create 2 type methods to handle persistence functionality. Since these functions are called on the type itself, we'll add the class keyword in front of the func keyword. The first function will be called saveScene and will take 2 parameters, a custom ARView and a URL. Keep in mind that this URL will point to a location in the local file system. For now, we'll just add a print statement in our function. We'll have it say something like, save scene to local file system. The second function will be called loadScene and will also take 2 parameters, a custom ARView and a data object. The data object will be our ScenePersistenceData. Again, in this function add a print statement with a message, loadScene from local file system. For now, we're done with our ScenePersistenceHelper. We'll definitely revisit to add the actual functionality for these 2 type methods. Next, we'll navigate to the SceneManager class in ARWContainer.Swift. Below the 2 published properties, we'll create 2 new ones. We'll create a Boolean variable called shouldSaveScene to filesystem and initialize it to false. This variable will serve as a flag to trigger SaveScene to filesystem function. The second variable will be called shouldLoadScene from filesystem, and will also be a boolean initialized to false. Next, we'll work on a method for ARViewContainer to handle persistence requests, based on these aforementioned boolean variables. Scroll down to our ARViewContainer extension, right below the updatePersistenceAvailability method. Create a new private method called handlePersistence. This method will take one parameter which will be a custom ARView type. From this method, we want to call our saveScene or loadScene helper methods. We'll create an if statement that checks the value of should saveScene to filesystem in our SceneManager instance. If it's true, we want to call the saveScene type method from our ScenePersistence We'll pass in our ARView and PersistenceUrl. Once the saveScene method has been called, we should reset the should saveScene to filesystem property to false. If we don't reset the variable, this function will continuously attempt to save the scene to file. If should saveScene to filesystem is false, we'll do an else if statement and check if should loadScene from filesystem is true. If it's true, we'll use a guard statement to safely unwrap the persistence data. Add a print statement if for some reason the persistence data is nil. Once we have our persistence data, we'll call the loadScene type method and pass along the ARView and persistence data. Because we are essentially resetting the scene when we load a scene from file, we should clear our anchor entities array in the SceneManager. And finally, similar to our previous if statement, reset the should loadScene from filesystem property to false. Before we move on to the next step, scroll up to the scene observer and make UI view, and call the handlePersistence method after our call to update persistence availability. Make sure to pass in our ARView. This completes the work we need to do in ARViewContainer.Swift. Next, we'll navigate to the SceneButton struct in ControlView.Swift. Inside the button action for saveScene, we'll set should saveScene to filesystem in our SceneManager to true. Similarly, inside the button action for the loadScene, we'll set should loadScene from filesystem in our SceneManager to true. Let's run the app to test our intermediate progress. Once we've mapped the scene and placed at least one object in it, we see that the saveScene button is displayed. When we press on it, we can see the print statements for pressing the button and actually calling the saveScene method from ScenePersistence For the next action item, we'll add functionality to the saveScene type method in ScenePersistence We'll navigate to the saveScene struct in ScenePersistenceHelper.Swift. There are 3 steps for this action item. First, we'll get the current world map from ARView.Session. The completion handler will provide us with a world map object and an error object. Second, inside our completion handler we'll safely unwrap world map using a guard statement. Note that if an error occurred, the world map will be nil. In this case, we'll print an error message to the console. However, this isn't the most elegant solution to notify the user that something didn't succeed. As a challenge, I encourage you to create a better way to alert the end user. For the third and final step, we'll use a do-catch statement to archive the map data and write it to the file system. Inside the do block, we can assign the archived data to a scene data constant. Next, we can write the scene data to the desired location on our file system using the PersistenceUrl. The write method can throw an error, so we'll make sure to use the try keyword. If the catch block catches an error, we'll print an error message. We are now done with our saveScene type method. Let's run the app to test our intermediate progress. Once we've mapped the scene and placed at least one object in it, we see that the saveScene button is displayed. When we press on it, we see that the loadScene button shows up. It looks like saving the scene data to file worked. For the next action item, we'll add functionality to the loadScene type method in ScenePersistence Before we get started on our function, let's import ARKit at the top of this file. Scroll back down to the loadScene function. There are 3 steps for this action item. First, we'll unarchive the ScenePersistence data and retrieve the ARWorldMap. We'll create a constant for our world map and use a function to return a world map. The world map contains all the data we need to restore a previously saved scene. Next, we can use a do-catch statement to unarchive the ScenePersistence data. If the guard statement fails, we'll create a fatal error with a message for the developer. We really don't want this to occur for an end user. If we've successfully unarchived the ScenePersistence data, we can return the world map. If an error is thrown by the unarchived object method, we'll catch that in our catch block and again create a fatal error with a message for the developer. Second, we'll need to navigate to Custom ARView to do some refactoring. Whenever we load a scene from file, we want to reset the session configuration. To do so, we'll create a default configuration computed property which will have an ARWorld tracking configuration type. Cut and paste everything but the last line from our configure method and paste it in the default configuration block. Make sure to return the config. In the configure method, change config to default configuration. For the third and final step, navigate back to the loadScene method in ScenePersistenceHelper.Swift. We need to reset the session configuration and load the world map as our initial world map. To do so, we'll create a new config constant and assign it the default configuration from ARView. Assign the world map to the initial world map of our new config. Run our new config with options.reset tracking and .remove existing anchors. We are now done with our loadScene type method. However, in its current state our app won't work properly. We'll work on fixing that next. And for the final action item, we'll update our codebase to allow placement of 3D models loaded from a persisted scene. This action item will contain a significant number of steps, so we'll create sub-action items. I'll first outline the sub-action items, and then we'll dive in. The first sub-action item will be to make our ModelsViewModel instance a state object and pass it into our environment. Previously, our ModelsViewModel was a local observed property in our Models by Category grid view in BrowseView.Swift. The second sub-action item will be to update our async_loadModelEntity method in Model.Swift to include a completion handler. This completion handler will run when an error has occurred or when the model entity has been successfully loaded. The third sub-action item will be to create a model anchor struct in placementSettings.Swift. We'll also update the type of the model confirmed for placement property from an optional model type to an array of model anchor. For the fourth sub-action item, we will make the necessary updates to our ARViewContainer.Swift file to allow placement of 3D models by the user or placement of 3D models by loading a saved scene from the file system. Let's get to work. The first sub-action item will be to make our ModelsViewModel instance a state object and pass it into our environment. Previously, our ModelsViewModel was a local observed property in our Models by Category grid view in BrowseView.Swift. The reason for making this change is that prior to adding scene persistence to our app, the only place we needed ModelsViewModel was in our BrowseView.Swift file. We will now need the ModelsViewModel in multiple places, so we'll add it to our environment instead. To do so, we'll start off by going to the main entry point of our app and create a new state object for our ModelsViewModel. Make sure to pass ModelsViewModel into our environment using the Environment Object modifier on Content View. Next, we'll navigate to the Models by Category grid view in BrowseView.Swift and make some updates. Remove the Observed Object property line and get access to the ModelsViewModel using the Environment Object property wrapper. Now that the property name has changed, update the instance name in the if statement in our forEach statement. We can also see that prior to adding scene persistence, we were fetching our 3D models and thumbnail images from Firebase Cloud Storage when the BrowseView appeared. However, this will no longer work for our app. We now want to load relevant assets as soon as the app opens, because the user might never open the BrowseView and instead restore a scene from file. If this happened, the assets wouldn't be available if we don't call fetchData when the app first opens. So let's remove the onAppear code. Next, we'll go to ContentView.Swift and make the necessary changes. We'll create a property for our ModelsViewModel using the Environment Object property wrapper. We'll call the fetchData method on our ModelsViewModel when the ZStack in our content view appears. This will guarantee that our assets will be available regardless of how assets are placed in the scene. Also scroll down to the preview provider and make sure to pass in an instance of ModelsViewModel in the environment. This completes everything we have to do for the first sub-action item. For the second sub-action item, we will update our async_loadModelEntity method in Model.Swift to include a completion handler. This completion handler will run when an error has occurred or when the model entity has been successfully loaded. Navigate to the async_loadModelEntity method in Model.Swift. Add the completion handler as a function parameter. In this case, our completion handler will expect two arguments, a Boolean property called completed and an optional error property. The completed Boolean property will only be true if the model entity was successfully loaded into memory. Of course, in this scenario the error will be nil. Next, we'll call the handler for our failure condition and pass in false and the error object. We'll also call the handler once the model entity has been successfully loaded. We'll pass in true and nil. For the next step, we'll navigate to the horizontal grid view in BrowseView.Swift. We'll update the code where we call async load model entity to use our completion handler. If completed is true, we'll assign model to the selected model property in placement settings. This completes the second subaction item. The third subaction item will be to create a model anchor struct in placement settings.swift. We'll also update the type of the model confirmed for placement property from an optional model type to an array of model anchor. Navigate to placement settings.swift. Right below our import statement, create a new struct called model anchor. This struct will have two properties, a model and an optional ARAnchor. You'll notice that ARAnchor isn't recognized because we haven't imported ARKit. Let's do so now. Before we move on, let's discuss why we need this struct. When the contents of an AR scene are saved to file, ARKit saves the state of the scene and any AR anchors in the scene. ARKit does not save any models or anchor entities. So, whenever we load a scene from file, we'll use this model and ARAnchor pair for placement. However, when the user selects a model for placement, the ARAnchor will be generated using ArrayCast. I hope this makes sense. Once you've completed this video, please look back at the code to make sure you have a good understanding of the why and the how of the things we did. Next, we'll completely remove the model confirmed for placement property in our placement settings struct. Below the recently placed property, we'll create a new variable for models confirmed for placement, which will be an array of model anchor. We'll initialize this property with an empty array. Now ask yourself, why did we change this property from a single model to an array of model anchor? When we load an AR scene from file, this scene could have multiple pieces of content in the scene, meaning it will have multiple AR anchors with attached content. We therefore need to use an array to keep track of all the content that has been confirmed for placement in the scene. For the last step in this subaction item, navigate to the Confirm Placement button in PlacementView.Swift. Remove the line with Model Confirmed for Placement. Create a new instance of Model Anchor and pass into the constructor the selected model for the model and nil for the anchor parameter. As mentioned before, we'll create an AR anchor using ArrayCast. Next, we can append our model anchor to models confirmed for placement. We are now done with the third subaction item. For the fourth subaction item, we will make the necessary updates to our ARViewContainer.Swift file to allow placement of 3D models by the user or placement of 3D models by loading a saved scene from the file system. Navigate to ARViewContainer.Swift. We'll start by importing ARKit. Next, right below our import statements, we'll create a global constant called anchorNamePrefix and assign it model dash. So why are we creating this constant? Well, whenever we place AR content in our scene, we'll use an AR anchor to create an anchor entity to which we'll attach our model entity. However, these won't be the only AR anchors in the scene. ARKit also adds AR anchors in the scene for detected planes, body tracking skeletons, etc. So by using an anchor name prefix for our anchor name property, we'll be able to distinguish our anchors from the system anchors. For the next step, we can gain access to our model's viewModel instance using the environmentObject property. When we load a scene from file, ARKit will restore the map and will add all anchors that were created in the saved scene. ARKit's AR session has a neat delegate method that is automatically called when new anchors are added to the scene. In order to conform to the AR session delegate, we'll use a SwiftUI coordinator. HackingWithSwift.com states that SwiftUI's coordinators are designed to act as delegates for UIKit view controllers. Delegates are objects that respond to events that occur elsewhere. In this case, our UIKit-based AR view needs to talk to our SwiftUI-based AR view controller. That's why we're using a coordinator. Create a new mark comment and label it AR session delegate plus coordinator. Create an extension to AR view container. Inside this extension, we'll create a new class called coordinator, which will be an NS object and will conform to AR session delegate. If you're not familiar with UIKit, NS object is the superclass for almost all other classes in UIKit. Our coordinator class will have a property called parent, which will be an ARViewContainer. We'll create an initializer for our coordinator which will take in an ARViewContainer object and initialize the corresponding instance property of the class. Below our coordinator class, we'll create a function called makeCoordinator which takes in no arguments and returns a coordinator object. Inside this function we'll construct a coordinator and pass in self, which is in this case the ARViewContainer. This makeCoordinator method is automatically called by SwiftUI. Back to our coordinator class. We can now access one of the AR session delegate methods. In this case, we're interested in implementing the didAddAnchors method. This method will be automatically called whenever the session adds new anchors. Inside the didAddAnchors delegate method, we have quite some work to do. First, we'll use a for-in statement to iterate over each anchor in the anchors array. ARAnchors have an optional name property. If an anchor has a name, we'll safely unwrap it and assign it to an anchor name constant. In the same conditional statement, we'll also check if the anchor name has the prefix anchor name prefix. Remember, we created this constant to distinguish our anchors from all other anchors created by the system. If we have an anchor name with the right prefix, we have an anchor of interest. For this anchor of interest, we'll extract the model name by dropping the anchor name prefix from the anchor name. For good measure, we'll add a print statement to log that AR session has found an anchor with model name. Next, we'll use a guard statement to obtain a reference to the model object obtained from the models array in models view model. We are essentially filtering through the models array looking for a model that matches the model name. Note that we access models view model through the parent object, which is in this case our AR view container. If we are unable to retrieve a model, we'll add a print statement and return. Once we have our model object, we can call async load model entity. When the model entity is loaded and the completion handler is called, completed will be true. We can then create a model anchor and pass in the model and anchor. We also want to add the model anchor to the models confirmed for placement array in placement settings. Finally, we'll add a print statement to log that a model anchor with name has been added. Our work on the coordinator is now complete. We can scroll up to our makeUI view method. Right below where we create our AR view, we'll assign context.coordinator to arview.session.delegate. Don't forget this, otherwise our AR view container won't receive delegate events. We are almost done, just a few more steps. Right below our place method, we'll create a new method called getTransformForPlacement. This function will take an AR view as parameter and will return an optional 4x4 matrix. This method will essentially handle the raycasting to find the transform needed for placing an object in the scene. We'll use a guard statement to make a raycast query. We want to make a raycast query originating from the center of the AR view. We'll use an estimated plane as the target for the raycast, and the target may be aligned in any way with respect to gravity. If we're unable to make the query, we'll return nil. Once we have a query, we'll initiate the raycast and obtain the nearest intersection with a real-world surface. If no results are available, we'll again return nil. Now that we have a raycast result, we'll return the world transform of this result. As the second to last step, we'll update the place method. Instead of 2 parameters, the place method will now take 3. We'll have a model entity, an AR anchor, and an AR view. Below the line where we add the model entity as a child of anchor entity, we'll assign an anchoring component to the anchoring property of anchor entity. This line of code essentially describes how the virtual content is anchored to the real world. That completes our updates to the place method. As the last step, we'll make changes to the updateScene method. Delete the if statement with confirmed model. Create a new if statement that assigns the last model anchor element in the models confirmed for placement array to a model anchor constant. In the same conditional statement, obtain the model entity from the model in model anchor. Inside the if statement, we'll safely unwrap the anchor from the model anchor instance and assign it to a constant. If this anchor exists, we know that it is being loaded from a previously saved scene. As a reminder, models placed by the user in the current session do not have an anchor object in the model anchor instance. We'll call the place method and pass in the model entity, anchor, and AR view. Next, we will call the addAnchor method on the AR view session and pass in our anchor. We will also append the model to the recently placed array in placement settings. For the else statement, we'll use an else if to get the transform for placement using our getTransformForPlacement method. If we're able to get a transform, we can proceed with creating an anchor for model placement. Create a constant to store the anchor name. As mentioned previously, the anchor name is the anchor name prefix concatenated with the model name. Next, we can create an AR anchor and pass in the anchor name and transform. Call the place method and pass in the model entity, anchor, and AR view. Like before, we'll add the anchor to the AR session and append the model to the recently placed array. And that's it. When you build the project, there should be no errors. Run the app. When we open the browse view, we notice that the app crashes. Apparently, placement settings cannot be found in the environment. To fix this, go to controlview.swift and navigate to the BrowseButtons struct.
We'll pass in placement settings to the BrowseView instance using the environment object modifier.
Our app should now be functioning properly.
Let's run it again and test the scene persistence functionality. We'll move around our device to map the environment and add several 3D models to our scene.
Then, we'll select the scene mode and save the scene. I'll stop the app from running and rerun it. We'll switch to scene mode and select the loadScene button. We'll move the device around to make sure it is able to map enough of our environment, and within a few seconds our previous scene should be restored. As you can see, scene persistence is a really powerful feature, and will likely be present in every compelling AR experience. A word of caution though. This app currently doesn't have a proper user experience to guide the user in restoring a scene. In order for the scene to be restored, the user needs to be in the same space with a similar perspective as when the scene was saved. As a challenge, I encourage you to make it more intuitive for the end user to use scene persistence. It would also be a great idea to allow the user to save multiple scenes to file. And that's it for this video. Thank you for watching, and until the next time.